Okay, I think we'll get started. So today we're going to finish our study of ice chart related things, and this will end with the topic of weak electrolytes. So we didn't spend a lot of time in lecture, but you had read in your book about the solubility rules, and those were just sort of rules of thumb that helped you decide if something is soluble or not soluble. Well, now that we have ice charts and we know about equilibrium constants, we can put a more quantitative number to the solubility. And basically what we have is a solid going to aqueous ion, and we write the K for that. And because this is a solid, we have just one in the denominator. And so our K, which we call an KSP, or solubility product, is simply the each ion raised to the stoichiometric factor. So this might be a little confusing right here, but I've got just a generic solid with not necessarily one-to-one oxidation numbers. And so we've got some kind of stoichiometric ratio here for the solid. And as that dissolves, then we see we're going to get NC, N cation, amount of A, and that will have a Na oxidation state. Likewise, we'll get Na amount of anion, and that will have an NC oxidation state. Let's give a real example here that might be a little bit more clear. Let's take iron 3 sulfate. And so with iron 3 sulfate, we have 2 irons and 3 sulfates. This will break up into, mistake here, 2 irons and 3 sulfates. So the 2 goes along here, right? And then the 3 comes up here as the oxidation state. 3 comes along here, and the 2 comes up as the oxidation state for our balanced reaction. And so if we were to write the K for this, let's do that right here. KSP will be concentration of iron squared, and then concentration of sulfate to the third power. Right? So that would be the solubility product for that. Okay. Well, let's do an example. Let's do calcium hydroxide. So calcium is 2+, hydroxide 1-. Make that a little more clear here. And so that's going to break up and give us 2 hydroxides for every 1 calcium. And so this happens to have a KSP of 5.5 times 10 to the minus 5. Well, let's write that. What is KSP here? It's going to be calcium times hydroxide concentration squared. That's the equilibrium constant for this reaction. Now, we'll write an ice chart here, and you'll see it's a very simple ice chart because this doesn't show up in the ice chart. That's going to be 1 all the way down. So we're going to start with no amount of calcium or hydroxide, and then we will get X, 2X, X, 2X, and we can write that like, 2X squared. So here's our calcium concentration in equilibrium. Here is our hydroxide, right? It's 2X, so really easy to make a mistake here. 2X here and squared. We can solve for X, and we get the hydroxide concentration, and we'll get a POH from this, and then the pH would be 14 minus the log of the hydroxide concentration, which gives us a pH of 12.6 here. And we know this is a base, and so we would expect to get a high pH there. I'm going to say one word of caution here. This isn't exactly true, right? We know the auto dissociation of water, so the base amount of this is 10 to the minus 7. So if the KSP is very small, then we would want to include the 1 times 10 to the minus 7. But here it's good enough to just call that 0. Okay. Now let's put a little twist on this. Let's say we are not going to dissolve this in pure water, but we're going to dissolve it in a salt water solution that has a common ion. And so we're going to get a common ion effect here, as we've seen before. And so let's take the example of trying to dissolve lead chloride into 0.1 molar potassium chloride. The KSP for lead chloride is 1 times 6 times 10 to the minus 5. Potassium chloride is completely soluble, so those are broken up into potassium and chloride. So that tells us that in the ice chart, we have a common ion here of the chlorine, and its initial concentration is coming from the potassium chloride. But that matters because that will impact the final equilibrium expression, and indeed that changes the value. We write the KSP equation now like this. This is our equilibrium constant, and we get an X value for that. And that's representing then the lead concentration and the chloride concentration. Okay, well, let's continue with this idea, but now let's check out the solubility in acid. Now, in acids, it affects the solubility, and we're going to look in particular about the solubility where we are working with an acid that has the same anion. So again, we're having a common ion effect here, but we're in this special case of an acid. So we write the Ka for the acid like this. Wait, that's what we've been doing before. And we're going to write something different now. We're going to write the fraction. This is the fraction of anion in solution. So that's defined to be the free anion over the free anion plus that bound with a proton. Well, we can make a little arrangement here by dividing top and bottom by H plus over HA, H plus over HA, top and bottom. And then what do I get here? Well, I get K here, and I get K here. Oops, should get H here. And I'm left over with a plus H down here. So this works itself out to be Ka over Ka plus H concentration. So that's a fraction of anion. And if we try to dissolve then a salt with the same anion in HA, then the KSP for that, and we won't work this out, I'll just tell you this here. The KSP for that is this, whoops, man, lots of mistakes here. Is this. Okay. And so here's how we would calculate the KSP. So let's do a practice example. Let's say this has a KSP of 2.06 times 10 to the minus 9, and we're going to do this at a pH of 4 in HA solution, and HA has a Ka of 6.3 times 10 to the minus 5. Well, let's first calculate the fraction of ion. So that's Ka over Ka plus H plus concentration. We're at a pH of 4. That means we're 1 times 10 to the minus 4. So here, if we work that out, is our fraction of ion in solution. Okay, well, now let's solve this equation for m squared. So I'm going to just bring this over here, take the square root. So it's KSP divided by that, take the square root, and we get 7.3 times 10 to the minus 5 molar. I should probably be careful and put the units on here. Now let's compare that with pure water, and we see that we get an increase in the solubility by a little bit. In pure water, we would get 4.5 times 10 to the minus 5 molar. Okay, so your book won't have these problems. It'll have up through here, so get a lot of good practice there. The homework that I've got has a bit of practice with that, and then it's got a little bit of practice with this solubility in acids as well. All right, so that's weak electrolytes. Very much the same idea, just in the context of a solid dissolving in water. But yet we still think about the equilibrium constant, we still do the ice charts, and we're able to utilize all the techniques that we've had from before. So common ion effect comes in. Here we have a combination of two Ks. So that complicates the matter a little bit. All right, so that's it, and we'll be heading on now to thinking about these ions. How do they solvate into solution? So we're going to shift gears a little bit, but we'll still be talking about ions in solution. So that will be what's coming up next.